Accelerating self-play learning in Go. Abstract. By introducing several improvements to the AlphaZero process and architecture, we greatly accelerate self-play learning in Go, achieving a 50x reduction in computation over comparable methods. Like AlphaZero and replications such as OpenGo and Leela Zero, our bot KataGo only learns from neural net-guided Monte Carlo tree search self-play. But whereas AlphaZero required thousands of TPUs over several days and ELF required thousands of GPUs over 2 weeks, KataGo surpasses ELF's final model after only 19 days on fewer than 30 GPUs. Much of the speedup involves non-domain specific improvements that might directly transfer to other problems. Further gains from domain-specific techniques reveal the remaining efficiency gap between the best methods and purely general methods such as AlphaZero. Our work is a step towards making learning in state spaces as large as Go possible without large-scale computational resources. Introduction. In 2017, DeepMind's AlphaGo Zero demonstrated that it was possible to achieve superhuman performance in Go without reliance on human strategic knowledge or pre-existing data. Subsequently, DeepMind's AlphaZero achieved comparable results in chess and shogi. However, the amount of computation required was large, with DeepMind's main reported run for Go using 5,000 TPUs for several days, totaling about 41 TPU years. Similarly, OpenGo, a replication by Facebook, used 2,000 V100 GPUs for about 13 to 14 days or about 74 GPU years, to reach top levels of performance. In this paper, we introduce several new techniques to improve the efficiency of self-play learning, while also reviving some pre-AlphaZero ideas in ComputerGo and newly applying them to the AlphaZero process. Although our bot KataGo uses some domain-specific features and optimizations, it still starts from random play and makes no use of outside strategic knowledge or pre-existing data. It surpasses the strength of OpenGo after training on about 27 V100 GPUs for 19 days, a total of about 1.4 GPU years, or about a factor of 50 reduction. And by a conservative comparison, KataGo is also at least an order of magnitude more efficient than the multi-year-long online distributed training project Leela Zero. Our code is open source, and superhuman trained models and data from our main run are available online too. We make two main contributions. First, we present a variety of domain-independent improvements that might directly transfer to other AlphaZero-like learning or to reinforcement learning more generally. These include, 1. A new technique of playout cap randomization to improve the balance of data for different targets in the AlphaZero process. 2. A new technique of policy target pruning that improves policy training by decoupling it from exploration in MCTS. 3. The addition of a global pooling mechanism to the neural net, agreeing with research elsewhere on global context in image tasks such as by Hu et al. 2018. And 4. A revived idea from supervised learning and Go to add auxiliary policy targets from future actions tried by Tian and Zhu 2016, which we find transfers easily to self-play and could apply widely to other problems in reinforcement learning. Second, our work serves as a case study that there is still a significant efficiency gap between AlphaZero's methods and what is possible from self-play. We find non-trivial further gains from some domain-specific methods. These include auxiliary ownership and score targets, similar to those in Wu et al. 2018, and which actually also suggest a much more general meta-learning heuristic, that predicting subcomponents of desired targets can greatly improve training. We also find that adding some game-specific input features still significantly improves learning, indicating that though AlphaZero succeeds without them, it is also far from obsoleting them. In Section 2 we summarize our architecture. In Sections 3 and 4 we outline the general techniques of playout cap randomization, policy target pruning, global pooling, and auxiliary policy targets, followed by domain-specific improvements including ownership and score targets and input features. In Section 5 we present our data, including comparison runs showing how these techniques each improve learning and all similarly contribute to the final result. Basic architecture and parameters. Although varying in many minor details, KataGo's overall architecture resembles the AlphaGo Zero and AlphaZero architectures. KataGo plays games against itself using Monte Carlo tree search (MCTS) guided by a neural net to generate training data. Search consists of growing a game tree by repeated playouts. Playouts start from the root and descend the tree, at each node end choosing the child C that maximizes. Where V C is the average predicted utility of all nodes in C's subtree, P C is the policy prior of C from the neural net, N C is the number of playouts previously sent through child C, and CPUCT equals 1.1. Upon reaching the end of the tree and finding that the next chosen child is not allocated, the playout terminates by appending that single child to the tree. 3. Like AlphaZero, to aid discovery of unexpected moves, KataGo adds noise to the policy prior at the root. P C equals 0.75 pro C plus 0.25 eta, where eta is a draw from a Dirichlet distribution on legal moves with parameter alpha equals 0.03192 n C, where n is the total number of legal moves. This matches AlphaZero's alpha equals 0.03 on the empty 19x19 Go board while scaling to other sizes. KataGo also applies a softmax temperature at the root of 1.03, an idea to improve policy convergence stability from psi, another AlphaGo Zero replication. The neural net guiding search is a convolutional residual net with a pre-activation architecture, with a trunk of B residual blocks with C channels. Similar to Leela Zero, KataGo began with small nets and progressively increased their size, concurrently training the next larger size on the same data and switching when its average loss caught up to the smaller size. In KataGo's main 19-day run, B, C began at 696 and switched to 10, 128, 15, 192, and 20, 256, at roughly 0.75 days, 1.75 days, and 7.5 days, respectively. The final size matches that of AlphaZero and ELF. The neural net has several output heads. Sampling positions from the self-play games, a policy head predicts probable good moves while a game outcome value head predicts if the game was ultimately won or lost. The loss function is where R element of win, loss is the outcome for the current player, Z is a one-hot encoding of it, Z is the neural net's prediction of Z, M ranges over the set of possible moves, pi is a target policy distribution derived from the playouts of the MCTS search, pi is the prediction of pi, CL2 equals 3e-5 sets an L2 penalty on the model parameters theta, and CG equals 1.5 is a scaling constant. As described in later sections, we also add additional terms corresponding to other heads that predict auxiliary targets. Training uses stochastic gradient descent with a momentum decay of 0.9 and a batch size of 256, the largest size fitting on one GPU. It uses a fixed per sample learning rate of 6e-5, except that the first 5 million samples, merely a few percent of the total steps, use a rate of 2e-5 to reduce instability from early large gradients. In KataGo's main run, the per sample learning rate was also dropped to 6e-6 starting at about 17.5 days to maximize final strength. Samples are drawn uniformly from a growing moving window of the most recent data, with window size beginning at 250,000 samples and increasing to about 22 million by the end of the main run. See Appendix C for details. Training uses a version of stochastic weight averaging. Every roughly 250,000 training samples, a snapshot of the weights is saved, and every 4 snapshots, a new candidate neural net is produced by taking an exponential moving average of snapshots with decay equals 0.75, averaging 4 snapshots of lookback. Candidate nets must pass a gating test by winning at least 100 out of 200 test games against the current net to become the new net for self-play. See Appendix E for details. In total, KataGo's main run lasted for 19 days using a maximum of 28 v100 GPUs at any time, averaging 26 to 27, and generated about 241 million training samples across 4.2 million games. Self-play games used Trompe-Taylor rules modified to not require capturing stones within pass-alive territory 4. Suicide, and Comey rules also varied from Trompe-Taylor randomly, and some proportion of games were randomly played on smaller boards 5. See Appendix D for other details. Major general improvements. 3.1 Playout cap randomization. One of the major improvements in KataGo's training process over AlphaZero is to randomly vary the number of playouts on different turns to relieve a major tension between policy and value training. In the AlphaZero process, the game outcome value target is highly data limited, with only one noisy binary result per entire game. Holding compute fixed, it would likely be beneficial for value training to use only a small number of playouts per turn to generate more games, even if those games are of slightly lower quality. For example, in the first version of AlphaGo, self-play using only a single playout per turn, i.e., directly using the policy, was still of sufficient quality to train a decent value net. However, informal prior research by Forston 2019 has suggested that at least in Go, ideal numbers of playouts for policy learning are much larger, not far from AlphaZero's choice of 800 playouts per move. Although the policy gets many samples per game, unless the number of playouts is larger than ideal for value training, the search usually does not deviate much from the policy prior, so the policy does not readily improve. We introduce playout cap randomization to mitigate this tension. On a small proportion p of turns, we perform a full search, stopping when the tree reaches a cap of n nodes, and for all other turns we perform a fast search with a much smaller cap of n less than n. Only turns with a full search are recorded for training. For fast searches, we also disable Dirichlet noise and other explorative settings, maximizing strength. For KataGo's main 19-day run, we chose p equals 0.25 and n equals 600, 100 initially, annealing up to 1,000, 200 after the first 2 days of training. Because most moves use a fast search, more games are played, improving value training. But since n is small, fast searches cost only a limited fraction of the computation time, so the drop in the number of good policy samples per computation time is not large. The ablation studies presented in section 5.2 indicate that playout cap randomization indeed outperforms a variety of fixed numbers of playouts. 3.2 Forced playouts and policy target pruning. Like AlphaZero and other implementations such as ELF and Leela Zero, KataGo uses the final route playout distribution from MCTS to produce the policy target for training. However, KataGo does not use the raw distribution. Instead, we introduce policy target pruning, a new method which enables improved exploration via forced playouts. We observed in informal tests that even if a Dirichlet noise move was good, its initial evaluation might be negative, preventing further search and leaving the move undiscovered. Therefore, for each child C of the route that has received any playouts, we ensure it receives a minimum number of forced playouts based on the noise policy and the total sum of playouts so far. We do this by setting the MCTS selection urgency PUCT C to infinity whenever a child of the route has fewer than this many playouts. The exponent of 1/2 less than 1 ensures that forced playouts scale with search but asymptotically decay to a zero proportion for bad moves, and k equals 2 is large enough to actually force a small percent of playouts in practice. However, the vast majority of the time, noise moves are bad moves, and in AlphaZero, since the policy target is the playout distribution, we would train the policy to predict these extra bad playouts. Therefore, we perform a policy target pruning step. In particular, we identify the child C with the most playouts, and then from each other child C, we subtract up to n forced playouts so long as it does not cause PUCT C greater than equals PUCT C, holding constant the final utility estimate for both. This subtracts all extra playouts that normal PUCT would not have chosen on its own, unless a move was found to be good. Additionally, we outright prune children that are reduced to a single playout. See Figure 1 for a visualization of the effect on the learned policy. Figure 1, log policy of 10 block nets, white to play. Left, trained with forced playouts and policy target pruning. Right, trained without. Dark, red through bright green ranges from about p equals 2e minus 4 to p equals 1. Pruning reduces the policy mass on many bad moves near the edges. The critical feature of such pruning is that it allows decoupling the policy target in AlphaZero from the dynamics of MCTS or the use of explorative noise. There is no reason to expect the optimal level of playout dispersion in MCTS to also be optimal for the policy target and the long-term convergence of the neural net. Our use of policy target pruning with forced playouts, though an improvement, is only a simple application of this method. We are eager to explore others in the future, including alterations to the PUCT formula itself. 3.3 Global pooling. Another improvement in KataGo over earlier work is from adding global pooling layers at various points in the neural network. This enables the convolutional layers to condition on global context, which would be hard or impossible with the limited perceptual radius of convolution alone. In KataGo, given a set of C channels, a global pooling layer computes 1 the mean of each channel, 2 the mean of each channel scaled linearly with the width of the board, and 3 the maximum of each channel. This produces a total of 3 C output values. These layers are used in a global pooling bias structure consisting of input tensors X shape B times CX and G shape B times CG. A batch normalization layer and ReLU activation applied to G output shape B times CG. A global pooling layer output shape 3CG. A fully connected layer to CX output shape CX. Channel-wise addition with X output shape B times CX. Figure 2, global pooling bias structure, globally aggregating values of one set of channels to bias another set of channels. This structure follows the first convolution layer of 2 to 3 of the residual blocks in KataGo's neural nets, and the first convolution layer in the policy head. It is also used in the value head with a slight further modification. See Appendix A for details. In Section 5.2 our experiments show that this greatly improves the later stages of training. As Go contains explicit non-local tactics (CO), this is not surprising. But global context should help even in domains without explicit non-local interactions. For example, in a wide variety of strategy games, strong players, when winning, alter their local move preferences to favor simple options, whereas when losing they seek complication. Global pooling allows convolutional nets to internally condition on such global context. The general idea of using global context is by no means novel to our work. For example, Hu et al. 2018 have introduced a squeeze and excitation architecture to achieve new results in image classification. Although their implementation is different, the fundamental concept is the same. And though not formally published, Squeeze-Excite-like architectures are now in use in some online AlphaZero related projects, and we look forward to exploring it ourselves in future research. 3.4 Auxiliary policy targets. As another generalizable improvement over AlphaZero, we add an auxiliary policy target that predicts the opponent's reply on the following turn to improve regularization. This idea is not entirely new, having been found by Tian and Zhu in Facebook's bot Dark Forest to improve supervised move prediction, but as far as we know, KataGo is the first to apply it to the AlphaZero process. We simply have the policy head output a new channel predicting this target, adding a term to the loss function. Where PIOP is the policy target that will be recorded for the turn after the current turn, PIOP is the neural net's prediction of PIOP, and WOPP equals 0.15 weights this target only a fraction as much as the actual policy, since it is for regularization only and is never actually used for play. We find in section 5.2 that this produces a modest but clear benefit. Moreover, this idea could apply to a wide range of reinforcement learning tasks. Even in single-agent situations, one could predict one's own future actions, or predict the environment, treating the environment as an agent. Along with section 4.1, it shows how enriching the training data with additional targets is valuable when data is limited or expensive. We believe it deserves attention as a simple and nearly costless method to regularize the AlphaZero process or other broader learning algorithms. 4 major domain-specific improvements. 4.1 Auxiliary ownership and score targets. One of the major improvements in KataGo's training process over AlphaZero comes from adding auxiliary ownership and score prediction targets. Similar targets were earlier explored in work by Wu et al. 2018 in supervised learning, where the authors found improved mean-squared error on human game result prediction and mildly improved the strength of their overall bot, CGI. To our knowledge, KataGo is the first to publicly apply such ideas to the reinforcement learning-like context of self-play training in Go 7. While the targets themselves are game-specific, they also highlight a more general heuristic underemphasized in transfer and multitask learning literature. As observed earlier, in AlphaZero, learning is highly constrained by data and noise on the game outcome prediction. But although the game outcome is noisy and binary, it is a direct function of finer variables, the final score difference and the ownership of each board location 8. Decomposing the game result into these finer variables and predicting them as well should improve regularization. Therefore, we add these outputs and 3 additional terms to the loss function. SS5 ownership loss, where O L P element of 0, 0.5, indicates if L is finally owned by P, or is shared. O is the prediction of O, and WO equals 1.5 B2 where B element of is the board width. Score belief loss PDF, where PS is a one-hot encoding of the final score difference, PS is the prediction of PS, and WSPDF equals 0.02. Score belief loss CDF, where WSCDF equals 0.02. While the PDF loss rewards guessing the score exactly, this CDF loss pushes the overall mass to be near the final score. We show in our ablation runs in section 5.2 that these auxiliary targets noticeably improve the efficiency of learning. This holds even up through the ends of those runs. Though shorter, the runs still reach a strength similar to human professional, well beyond where the neural net must have already developed a sophisticated judgment of the board. It might be surprising that these targets would continue to help beyond the earliest stages. We offer an intuition: consider the task of updating from a game primarily lost due to misjudging a particular region of the board. With only a final binary result, the neural net can only guess at what aspect of the board position caused the loss. By contrast, with an ownership target, the neural net receives direct feedback on which area of the board was mispredicted, with large errors and gradients localized to the mispredicted area. The neural net should therefore require fewer samples to perform the correct credit assignment and update correctly. As with auxiliary policy targets, these results are consistent with work in transfer and multitask learning showing that adding targets or tasks can improve performance. But the literature is scarcer in theory on when additional targets may help. See Zhang and Yang 2017 for discussion, as well as Bingle and Skal 2017 for a study in NLP domains. Figure 3: Visualization of ownership predictions by the trained neural net. Our results suggest a heuristic: whenever a desired target can be expressed as a sum, conjunction, or disjunction of separate subevents, or would be highly correlated with such subevents, predicting those subevents is likely to help. This is because such a relation should allow for a specific mechanism, that gradients from a mispredicted sub-event will provide sharper, more localized feedback than from the overall event, improving credit assignment. We are likely not the first to discover such a heuristic. And of course, it may not always be applicable. But we feel it is worth highlighting both for practical use and as an avenue for further research, because when applicable, it is a potential path to study and improve the reliability of multitask learning approaches for more general problems. 4.2 Game-specific features. In addition to raw features indicating the stones on the board, the history, and the rules and komi in effect, KataGo includes a few game-specific higher-level features in the input to its neural net, similar to those in earlier work. These features are liberties, komi parity, pass-alive regions, and features indicating ladders, a particular kind of capture tactic. See Appendix A for details. Additionally, KataGo uses two minor Go-specific optimizations, where after a certain number of consecutive passes, moves in pass-alive territory are prohibited, and where a tiny bias is added to favor passing when passing and continuing play would lead to identical scores. Both optimizations slightly speed up the end of the game. To measure the effect of these game-specific features and optimizations, we include in Section 5.2 an Ablation Run that disables both ending optimizations and all input features other than the locations of stones, previous move history, and game rules. We find they contribute noticeably to the learning speed, but account for only a small fraction of the total improvement in KataGo. 5 results. 5.1 Testing versus ELF and Leela Zero. We tested KataGo against ELF and Leela Zero 0.17 using their publicly available source code and trained networks. We sampled roughly every fifth Leela Zero neural net over its training history from LZ30 through LZ225, the last several networks well exceeding even ELF's strength. Between every pair of Leela Zero nets fewer than 35 versions apart, we played about 45 games to establish approximate relative strengths of the Leela Zero nets as a benchmark. We also sampled KataGo over its training history, for each version playing batches of games versus random Leela Zero nets with frequency proportional to the predicted variance p of the game result. The winning chance p was continuously estimated from the global Bayesian maximum likelihood ELO based on all game results so far 9. This ensured that games would be varied yet informative. We also ran ELF's final V2 neural network using Leela Zero's Engine 10, with ELF playing against both Leela Zero and KataGo using the same opponent sampling. Games used a 19x19 board with a fixed 7.5 komi under Trompe-Taylor rules, with a fixed 1600 visits, resignation below 2% win rate, and multi-threading disabled. To encourage opening variety, both bots randomized with a temperature of 0.2 in the first 20 turns. Both also used a lower confidence bound move selection method to improve match strength. Final ELO ratings were based on the final set of about 21,000 games. To compare the efficiency of training, we computed a crude indicative metric of total self-play computation by modeling a neural net with B blocks and C channels as having cost BC2 per query 11. For KataGo we just counted self-play queries for each size and multiplied. For ELF, we approximated queries by sampling the average game length from its public training data and multiplied by ELF's 1600 playouts per move, discounting by 20% to roughly account for transposition caching. For Leela Zero we estimated it similarly, also interpolating costs where data was missing 12. Leela Zero also generated data using ELF's prototype networks, but we did not attempt to estimate this cost 13. KataGo compares highly favorably with both ELF and Leela Zero. Shown in Figure 4 is a plot of ELO ratings versus estimated compute for all three. KataGo outperforms ELF in learning efficiency under this metric by about a factor of 50. Leela Zero appears to outperform ELF as well, but the ELO ratings would be expected to unfairly favor Leela since its final network size is 40 blocks, double that of ELF, and the ratings are based on equal search nodes rather than GPU cost. Additionally, Leela Zero's training occurred over multiple years rather than ELF's 2 weeks, reducing latency and parallelization overhead. Yet KataGo still outperforms Leela Zero by a factor of 10 despite the same network size as ELF and a similarly short training time. Early on, the improvement factor appears larger, but partly this is because the first 10% to 15% of Leela Zero's run contained some bugs that slowed learning. Figure 4 to 1600 visit ELO progression of KataGo blue, leftmost versus Leela Zero red, center, and ELF green diamond. X-axis, self-play cost in billions of equivalent 20-block x 256 channel queries. Note the log scale. Leela Zero's costs are highly approximate. KataGo match results versus ELF, with the implied ELO difference plus or minus 2 std. Deviations of confidence. We also ran 3 400 game matches on a single V100 GPU against ELF using ELF's native engine. In the first, both sides used 1600 playouts, move with no batching. In the second, KataGo used 9's move 16 threads, max batch size 16, and ELF used 16,000 playouts, move batch size 16, which ELF performs in 9 seconds. In the third, we doubled ELF's batch size, improving its nominal speed to 7.5 s move, and lowered KataGo to 7.5 s move. As summarized in Table 1, in all 3 matches KataGo defeated ELF, confirming its strength level at both low and high playouts and at both fixed search and fixed wall clock time settings. 5.2 Ablation Runs. To study the impact of the techniques presented in this paper, we ran shorter training runs with various components removed. These ablation runs went for about 2 days each, with identical parameters except for the following differences. Fixed n replaces playout cap randomization with a fixed cap n element of 100, 150, 200, 250, 600. For n equals 600, the window size was also doubled, as an informal test without doubling showed major overfitting due to lack of data. No force TP removes forced playouts and policy target pruning. No G-pool removes global pooling from residual blocks and the policy head except for computing the pass output. No PO removes the auxiliary policy target. No VO removes the ownership and score targets. No Go feat removes all game-specific higher-level input features and the minor optimizations involving passing listed in section 4.2. We sampled neural nets from these runs together with KataGo's main run, and evaluated them the same way as when testing against Leela Zero and ELF, playing 19 by 19 games between random versions based on the predicted variance p(1-p) of the result. Final LOs are based on the final set of about 147,000 games. Note that these LOs are not directly comparable to those in section 5.1. Figure 5, KataGo's main run versus fixed runs. X-axis is the cumulative self-play cost in millions of equivalent 20-block x 256 channel queries. As shown in Figure 5, playout cap randomization clearly outperforms a wide variety of possible fixed values of playouts. This is precisely what one would expect if the technique relieves the tension between the value and policy targets present for any fixed number of playouts. Interestingly, the 600 playout run showed a large jump in strength when increasing neural net size. We suspect this is due to poor convergence from early overfitting not entirely mitigated by doubling the training window. Figure 6, KataGo's main run versus no G-pool, no force TP, no PO. X-axis is the cumulative self-play cost in millions of equivalent 20-block x 256 channel queries. Figure 7, KataGo's main run versus no VO, no Go feat. X-axis is the cumulative self-play cost in millions of equivalent 20-block x 256 channel queries. As shown in Figure 6, global pooling noticeably improved learning efficiency, and forced playouts with policy target pruning and auxiliary policy targets also provided smaller but clear gains. Interestingly, all three showed little effect early on compared to later in the run. We suspect their relative value continues to increase beyond the 2-day mark at which we stopped the ablation runs. These plots suggest that the total value of these general enhancements to self-play learning, along with playout cap randomization, is large. As shown in Figure 7, removing auxiliary ownership and score targets resulted in a noticeable drop in learning efficiency. These results confirm the value of these auxiliary targets and the value, at least in Go, of regularization by predicting subcomponents of targets. Also, we observe a drop in efficiency from removing Go-specific input features and optimizations, demonstrating that there is still significant value in such domain-specific methods, but also accounting for only a part of the total speedup achieved by KataGo. See Table 2 for a summary. The product of the acceleration factors shown is approximately 9.1x. We suspect this is an underestimate of the true speedup since several techniques continued to increase in effectiveness as their runs progressed and the ablation runs were shorter than our full run. Some remaining differences with ELF and/or AlphaZero are likely due to infrastructure and implementation. Unfortunately, it was beyond our resources to replicate ELF and/or AlphaZero's infrastructure of thousands of GPUs, TPUs for a precise comparison, or to run more extensive ablation runs each for as long as would be ideal. Table 2, for each technique, the ELO of the ablation run emitting it as of reaching 2.5 G equivalent 20B x 256 C self-play queries approximately equals 2 days, and the factor increase in training time to reach that ELO. Factors are approximate and are based on shorter runs. 6 conclusions and future work. Still beginning only from random play with no external data, our bot KataGo achieves a level competitive with some of the top AlphaZero replications, but with an enormously greater efficiency than all such earlier work. In this paper, we presented a variety of techniques we used to improve self-play learning, many of which could be readily applied to other games or to problems in reinforcement learning more generally. Furthermore, our domain-specific improvements demonstrate a remaining gap between basic AlphaZero-like training and what could be possible, while also suggesting principles and possible avenues for improvement in general methods. We hope our work lays a foundation for further improvements in the data efficiency of reinforcement learning.